So if you have these two objects where one is orbiting, we tend to say that if one mass is much larger than the other mass, we tend to call it the central mass, like Moon going around the Earth, or even the Earth going around the Sun. The Sun is much larger than the Earth, so we'd consider it to be a central mass. But you're quite right. If I have two objects that are orbiting mutually around each other, there might be a center of mass directly in the middle, and in which case they'd orbit around that central mass. It actually does make it a little bit more difficult. We really can't analyze it in the way that we've suggested that you can analyze it if one mass is substantially smaller than the other. This really works best in the limit where M1 is much, much bigger than M2, okay? So that we can make the approximation that Fg equals Fc. So it really reveals the weakness in this. The weakness is that it really exists within these limits, okay? So if they happen to be equal in mass, they'd orbit around a central point, like directly in between. If you happen to have two objects where one is a little bit bigger than the other, but not so much so that this one is, you know, in the limit where it's much, much smaller than this one, where it's actually an appreciable size compared to this one, you would say that they orbit around the center of mass, and the center of mass for this system might be right here. Might not even be outside the surface of the planet. The center of mass for this system might be within the surface of the planet, and in that case what you'd see is the planet, and maybe a very large moon, would orbit around that center of mass, and what it would look like from the perspective of looking at the planet would be that the planet would kind of wobble, and would wobble around that point. You picture that? And it's good to be able to think about that, because it's actually what happens with our planet. Our planet actually, although it's much, much bigger than the moon, the center of mass for our planet and the moon is within the Earth's surface. So the center of mass for the Moon-Earth system isn't right within the center of the Earth. It's actually a little off the center of the Earth, which means that the Earth actually does wobble due to its rotation, mutual rotation with the moon around the center of mass between the moon and the Earth. That's something we don't really notice, but it's something that's there, okay? So it's nice to acknowledge reality a little bit. That's reality, okay? We're going to make an approximation in a limit where the mass of the moon is much smaller than the Earth. And we're going to carry that approximation forward, because this actually gets to be a fairly complicated system if we start thinking about rotation around the center of mass. Yep?
I'm confused as to like how the Earth wobbles, like side to side.
Yeah, side to side.
This
Side to side around its, if we claimed that was the north-south pole, the rotational axis, it would wobble around that south pole. You ever had a lopsided beach ball? They sell these things sometimes. Take a lopsided beach ball, and usually they have like a lead pack attached to one side of them, but within plastic. And you throw it through the air, and I think Kentucky Fried Chicken used to sell them. They called it an oopie ball, because it went whoop, 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 and it went, as it went through. Yeah, they sold it like it was kind of like a Happy Meal, but for chicken. I don't know, they got out of that business. But it was a fun little ball. You could take it to the beach and have fun with it. Yeah.
So wouldn't any smaller body orbiting around a larger body have a center of orbiting around that is slightly off of the center of the larger body?
Yeah. Yeah. Every.
In those cases, it would be unnoticeably small.
Yeah. All we're saying is that if the orbiting mass, the satellite, is in the limit much, much smaller than the central mass, what we call the central mass, then the center of mass for the system isn't that far off of the center of mass of the individual planet, so we don't think about it. It's an approximation. And you know, so many things in physics are approximations, like the fact that we neglect air resistance in most cases. It's an approximation. And so we're just building it up. And you want to take a nice university course in rotational dynamics, they'll go into that, like rotation in 3 dimensions, and they'll start talking about gyroscopic motion, and you'll have to deal with matrices to do it probably. But it's a wonderful study. It's just not where we're at right now. So we're going to make this approximation because it fits with high school. Yeah?
Do we ever have to graph the motion of something going around something else in a 3D plane?
No, we're not going to do any 3-dimensional
No,
graph.
not now, but would we ever have to for physics in like university?
Well, I can remember doing some nice 3-dimensional graphs that were time dependent for probability of location for atomic orbits, for example. And so I can imagine that you might do something like that with planets.
Different though, because that's just the probabilities to where they are in like a cluster of clouds.
Well, it's a wave function, but this is a wave function. It's just kind of a boring wave function,
Okay.
right? It's a repeating cycle. Yeah.